Today we will look at some problems about weirs and overflow spillways. So for the first problem, we know the width of a rectangular channel is 13.1 feet and the flow rate equals 72.7 cubic feet per second. And we need to determine the depth of water that would be produced upstream of a 3.28 feet high weir that is built across the floor of the channel. And also need to determine the velocity of the flow over the weir and assume the weir friction loss and the velocity head upstream are negligible. So first, we need to determine the critical depths. So we know the YC equals cubic root of Q square over the G times B square. This is equation 6.14 in the textbook. And from the problem, we know the Q equals 22.7 cubic feet per second, and the B equals 13.1 feet. So we can determine Y sub C critical depth equals 0.985 feet. Since we assume the wheel friction loss and the velocity head are negligible, so we can get that the water depth upstream of the weir, the H, equals 3/2 times critical depth plus the X. This is equation 8.7 in the textbook. And we know YC equals 0.985 feet. And X is the height of the weir. So we know X equals 3.28. So we can determine that the H, the water depth upstream of the weir, equals 4.76 feet. And we still need to determine the velocity of flow over the weir, and we know the V should be equal to the Q over the A, and A equals the Q over the B times Y sub C. So equals 17.7 cubic feet per second divided by the 13.1 feet times 0.985 feet. So we can determine the velocity should be equal to 5.63 feet per second. So we solved this problem. For the second problem, the energy gray line upstream of a weir is 2.6 meters above the channel bottom, and the 1.4 meter high, 5 meter wide weir resides in a rectangular channel carrying a flow of 10 cubic meters per second. We need to determine the actual coefficient of discharge in the weir equation considering the energy losses. Equation is 8.8c. And we also need to determine the amount of the energy loss in meters. So for frictionless weir, equation 8.8c is written as Q, the discharge per unit width, equals the flow rate divided by the B, equals 1.7 times HS to the power of 3/2. And we know the 1.7, this value is coefficient of discharge CD. And from the problem, we know that the actual coefficient of discharge for this problem is not 1.7. We need to determine this value. And the H sub S is the vertical distance from the weir crest to the upstream water level. So for this problem, the discharge per unit width Q should be equal to Q sub D times HS to the power of 3/2. And we know the flow rate of this problem should be equal to 10 cubic meters per second, and the B equals 5 meters. So we can determine the discharge per unit width should be equal to 2 meters squared per second. And ignoring the velocity hat, we know the h sub s should be equal to the h minus x. And from problem, we know h equals 2.6 meter, and the x is the height of the weir. From problem, we know x equals 1.4 meters, so we can determine the h sub s should be equal to 1.2 meters. And now we can determine the actual coefficient of discharge CD is 1.52 for this problem. And we still need to determine the amount of energy loss. So we balance the energy at the weir and upstream. We can get this equation. E sub UP, the energy at the upstream should be equal to the x, the height of the weir, plus the specific energy at the weir, plus the head loss. And we know the specific energy at the critical section should be equal to the 3/2 times y sub c. This is equation 6.8 in the textbook. So now this equation can be rewritten as E sub UP equals x plus the 3/2 times y sub c plus the head loss. And we know, y sub c equals cubic root of q squared over g, and we know the discharge per unit width we calculated before equals 2 meters squared per second. So we can determine y sub c critical depth should be equal to the 0.742 meters. And we know the height of the weir x is 1.4 meters, and we know the energy at the upstream E sub UP is 2.6 meters. So now we can determine the energy head loss, the head loss. HL should be equal to 0.087 meters. So we solved this problem. For the third problem, an overflow spillway for a small water supply reservoir needs to be designed. The spillway must be able to pass a design flood flow of 935 cubic feet per second. However, flooding upstream of the reservoir will occur if the water depths in the reservoir rise above the spillway crest by more than 4.2 feet. Can the design be accomplished if the spillway width is limited by site conditions to roughly 30 feet? If not, suggest some alternatives that would meet the existing design conditions, and assume an approximate spillway coefficient of 3.5. So first, we apply equation 8.9 in textbook and ignore the approach velocity. So we can get that the Q equals the C times L times the HS to the power of 3/2. And we know the spillway coefficient C equals 3.5, and the length equals 30 feet. And we know the HS equals 4.2 feet. So we can determine now the flow rate Q equals 904 cubic feet per second, and we know this value is less than the design flood flow, 935 cubic feet per second. So the design Q can be met under these conditions. So we need to give some alternatives that meet the existing design conditions. So there are two methods. The first method, we can determine the length of spillway that is needed. Again, the Q equals C times L times HS to the power of 3 over 2. And now we know the design flood flow rate equals 935 cubic feet per second, and the C equals 3.5, and the HS equals 4.2 feet. So now we can determine the length of the spillway should be equal to the 31 feet. And other method is determine the spillway coefficient that is needed. Again, the Q equals C times L times HS to the power of 3 over 2. And design the flood flow rate Q equals 935 cubic feet per second. And the original length of the spillway equals 30 feet. And the HS equals 4.2 feet. So now we can determine the coefficient, spillway coefficient C should be equal to the 3.62. So we can get a conclusion. Examine whether the spillway can be slightly lengthened, or the spillway coefficient can be improved to increase the flow. So now we solved this problem. For the last problem, as water moves through the hydraulic circle, water quality changes are common due to natural phenomenon or anthropogenic pollution. Using figure 11.1, describe how water quality changes occur during each phase of the hydraulic circle. So I think there is no standard answer for this problem. So I wrote some example here as your reference. So there are some examples on the first page, and there are some examples on the second page, and some examples on the third page.